Samples vary because a sample is only one possible draw from a larger population or process. Even if the underlying population truth is fixed, the particular people, events, or records you happen to observe will differ from sample to sample. This is not a mistake or a flaw. It is the normal consequence of randomness and partial observation. In practical terms, sample-to-sample variation shows up anytime you rerun a survey, extract a different time window, observe a different set of patients, or sample a subset of transactions. For example, if you repeatedly take a random sample of 1,000 individuals from the same population, the sample mean will change slightly each time because you are not selecting the exact same people. Another example is that a monthly rate for a rare event will bounce around even if the true underlying rate is stable, because the number of events is small and chance plays a larger role. A third example is that site-level percentages can fluctuate from quarter to quarter, especially for small sites, because a handful of outcomes can shift the percentage noticeably. The standard error is a summary of how much an estimate would vary across repeated samples under the same sampling process. It is not the spread of individual data points. It is the spread of the estimate itself. This distinction is one of the biggest conceptual steps in biostatistics because it separates variability in people from variability in your summary of people. For example, the standard deviation describes how spread out individual values are around the mean within a sample, such as how much individual ages vary. The standard error of the mean describes how much the sample mean would vary if you repeatedly drew new samples of the same size from the same population. Another example is a proportion. Individual outcomes are 0 or 1, but the estimated proportion has a standard error that reflects how much that estimated proportion would fluctuate across repeated samples. A third example is a rate based on person time. Events are discrete, but the estimated rate has a standard error that reflects uncertainty given the event count and exposure time. Standard error is therefore the core link between an estimate and how precise it is. Standard error gets smaller as sample size grows because larger samples provide more information about the population. This is why precision improves with larger denominators. The intuition is that random imbalances average out when you observe more units. For example, a mean calculated from 10 observations can move a lot if one extreme value appears, but a mean calculated from 10,000 observations barely changes from one additional value. Another example is a proportion based on 50 people. One additional yes changes the percentage by 2 points, while a proportion based on 5,000 people barely moves. A third example is a rare event rate. If there are only 3 events in a time window, the rate estimate will be unstable. But if there are 300 events, the rate becomes much more stable. This is why charts and tables should often show denominators and event counts, because they signal expected standard error and stability. Standard error is also shaped by how variable the underlying outcome is. Even with the same sample size, estimates are less precise when the outcome has more variability. For a mean, more spread in individual values leads to a larger standard error of the mean. For a proportion, the standard error depends on how close the proportion is to 0.5 versus near 0 or 1. Proportions near 0.5 tend to have larger standard errors for the same sample size because there is more uncertainty in a balanced outcome than in a very rare or very common outcome. For rates, fewer events relative to person time implies higher uncertainty because discrete event counts carry more random variability when counts are low. Examples include a highly variable cost outcome, producing wide uncertainty around the mean, a balanced binary outcome, producing a less precise proportion than a very rare outcome at the same sample size, and a low event count, producing a wide confidence interval around a rate. This is why both sample size and outcome variability matter for precision. In real data sets, the standard error also depends on the sampling design, not just the sample size. If observations are correlated within clusters, such as patients within clinics or students within schools, the effective information is less than the raw number of observations suggests, because cluster members are more similar to each other than to the population at large. This increases standard error compared with what you would compute under an independence assumption. Similarly, if weights are used to make a sample represent a population, variability can increase because weights amplify the influence of some observations. Examples include a survey with cluster sampling, where respondents within the same cluster share similarities, a multi-site dataset, where outcomes within a site are correlated due to shared practices, and a weighted survey where a small number of heavily weighted responses influence the estimate. In all these cases, a naive standard error based on simple random sampling can be too small, making results look overly certain. Finally, standard error is the foundation of confidence intervals and significance testing, but its most practical use is communicating precision. When you understand standard error, you can interpret whether differences are likely meaningful or mostly noise. For example, two subgroup proportions that differ by 2 percentage points might be meaningfully different in a very large sample with small standard errors, but the same 2-point difference might be indistinguishable from noise in a small sample with large standard errors. Another example is comparing rates across small areas. Apparent ranking differences can be mostly due to standard error differences rather than true underlying rate differences. A third example is time series monitoring. Month-to-month bumps in a rare event rate can be mostly standard error rather than a true trend. Standard error gives you a disciplined way to connect an estimate to how much you should trust its stability. The central limit theorem, CLT, is a foundational idea that explains why many common statistical methods work even when the underlying data are not perfectly normal. The CLT states that under certain conditions, the sampling distribution of a properly scaled sample mean becomes approximately normal as the sample size increases. The key phrase is sampling distribution. This is not saying the original data become normal. He is saying the distribution of the estimate, like the sample mean, across repeated samples becomes normal-like. This matters because normal-like sampling distributions allow you to build confidence intervals and perform hypothesis tests using familiar formulas. For example, individual costs might be highly skewed, but the mean cost across many independent samples of large size can have an approximately normal sampling distribution. Another example is that individual measurements can be irregular, but the average across a large sample can still behave predictably. A third example is that a sample proportion can have an approximately normal sampling distribution when the sample is large enough and not extremely close to 0 or 1. CLT intuition starts with the idea of averaging smoothing out randomness. When you take a mean, you combine many independent contributions. Extreme values still matter, but they are diluted by the number of observations. As sample size increases, the distribution of the mean tightens and becomes more symmetric. A practical way to picture it is that each sample mean is the result of many small random contributions, and when many independent contributions add together, the sum tends to look normal-like. For example, if you repeatedly take samples of 30, then 100, then 1,000 observations and compute the mean each time, the resulting means form a distribution that becomes more bell-shaped and more concentrated around the true population mean as sample size increases. Another example is the mean waiting time across a day of observations. Even if individual waiting times are skewed, the day's average may be fairly stable when there are many observations. A third example is the average score across a large cohort, which often looks stable and roughly normal-like across repeated cohorts. The CLT is also the reason standard error decreases with sample size, and it helps you understand the trade-off between sample size and uncertainty. For the mean, the standard error is connected to the standard deviation of individual values divided by the square root of sample size. The CLT supports this relationship by describing how the distribution of the mean shrinks as the sample grows. The square root pattern is important. To cut standard error in half, you generally need about 4 times the sample size. This is why very large sample increases can be required for modest gains in precision. For example, increasing from 100 to 400 observations reduces standard error by about half. Another example is that increasing from 1,000 to 4,000 can halve standard error again. A third example is that if an outcome is very variable, even large sample sizes may still yield standard errors that are not tiny. because the numerator variability remains large. The CLTLT helps you interpret why some estimates remain uncertain, even in fairly large samples. CLT conditions matter, and this is where it can fail or perform poorly. One major condition is independence or weak dependence. If observations are highly correlated, such as repeated measurements from the same person treated as independent or clustered observations within the same site, the effective sample size is smaller than the raw count, and the CLT-based normal approximation for the mean can be misleading without accounting for that correlation. Another major condition is that the outcome should have a finite variance, meaning the outcome is not so heavy-tailed that variability is mathematically unbounded. In many real settings, variance is finite, but heavy tails can still cause slow convergence to normality, meaning you need very large samples before the sampling distribution looks normal-like. A third condition is that the sample should not be dominated by a few extreme values that act like rare huge shocks, because those can make the mean unstable and the normal approximation unreliable at common sample sizes. The KLT can also fail in practice for proportions and counts when sample sizes are small or when the event is very rare or very common. A common rule of thumb idea is that normal approximation for a proportion works better when there are enough expected successes and enough expected failures, meaning both the numerator and the complement count are not tiny. When events are rare, the sampling distribution can be skewed and discrete, and methods that assume normality can perform poorly. Examples include rare adverse events in a small program, where month-to-month proportions are based on a few events, and the confidence interval can be asymmetric. Another example is small area rates where event counts are low, producing unstable estimates and distributions that are not well approximated by normal. A third example is binary outcomes near 0% or near 100%, where the distribution is bounded, and the normal approximation can produce confidence intervals that go below 0 or above 1 if not handled carefully. In these situations, alternative methods or transformations are often used to better reflect the true uncertainty. Small sample size is not the only reason the CLT can be unreliable. Non-random sampling and selection can also break the usefulness of CLT-based inference because the sampling variation you are describing may not reflect the actual uncertainty you care about. If a sample is biased, the mean can be very precise around the wrong value, and the CLT does not fix that. Examples include a survey with non-response bias where responders differ systematically from non-responders, a dataset that captures only service users when you want population inference, and a convenience sample from one site used to generalize to many sites. In these cases, the sampling distribution may still be approximately normal, but it will be centered around a biased estimate. That is why the CLT is about variability under a given sampling process, not about whether the sampling process produces an unbiased view of the target population. Finally, even when the CLT holds reasonably well, it is still good practice to use visuals and checks that align with what the data are doing. For means of skewed data, reporting medians and percentiles alongside means can keep interpretation grounded. For rare event rates, using methods that match counts and person time can provide more appropriate intervals and comparisons than normal approximations. For cluster data, using cluster-aware standard error methods or design-based methods can restore valid inference. Examples include using robust standard errors when correlation is present, using distribution-matched models for counts rather than treating them as normal, and using bootstrap resampling when the analytic standard error formula is uncertain. The KLT is a powerful backbone, but the professional habit is to treat it as an approximation with conditions, not as an automatic guarantee. Precision is about how tightly your estimates would cluster if you repeated the same process many times. Accuracy is about how close your estimate is to the true value you are trying to measure. These are different concepts, and both matter in biostatistics because you can be very consistent and still be consistently wrong. Precision is primarily controlled by random variability and sample size, which is why it is connected to standard error and confidence intervals. Accuracy is primarily controlled by systematic issues like bias, measurement error, selection, confounding, and misclassification. For example, you can have a very large sample that produces a narrow confidence interval, which indicates high precision, but if the sample is biased or the measure is flawed, the estimate may be inaccurate. Another example is a small sample that produces a wide confidence interval, which indicates low precision, but the estimate can still be accurate if it happens to land close to the truth. A third example is a consistent data entry error that shifts all values upward, producing precise but inaccurate summaries. Precision is easiest to see in repeated sampling intuition or in the size of uncertainty measures. A small standard error or narrow confidence interval reflects high precision. Increasing sample size typically increases precision because it reduces random sampling variability. For example, an estimated proportion based on 10,000 observations will usually be much more precise than the same proportion based on 100 observations. Another example is that a rate based on 200 events will be more precise than a rate based on 5 events because event counts drive random variability. A third example is that an average computed from many independent observations will be more stable from month to month than an average computed from a small number of observations. Precision is about repeatability in the statistical sense. If you could rerun the same study or collect the same type of data again, high precision means you would get a similar estimate most of the time. Accuracy depends on whether your estimate is centered on the truth, not on how narrow the interval is. In practical work, threats to accuracy often come from selection and measurement. Selection affects accuracy when the observed sample is not representative of the target population in ways related to the outcome or key predictors. For example, a survey estimate can be inaccurate if non-responders differ systematically from responders. Another example is using clinical records to estimate population prevalence, which can be inaccurate because people who seek care differ from those who do not. A third example is program evaluation data that include only participants who remain engaged, which can overstate success if dropouts are not random. Measurement affects accuracy when variables are recorded incorrectly or inconsistently, such as misclassified outcomes, inconsistent coding across sites, or missing data patterns that are not random. These issues can shift the estimate away from the truth even if the estimate is very precise. A useful way to remember the difference is that precision is about random error, while accuracy is about bias plus random error. Random error makes estimates bounce around. Bias shifts estimates in a consistent direction. You can reduce random error by increasing sample size, improving measurement reliability, or using more efficient estimators. Reducing bias often requires improving design, measurement, and definitions rather than simply collecting more data. For example, collecting more data from a biased sampling frame increases precision around a biased value. Another example is that adding more observations does not fix a misclassification problem if the classification rule is wrong. It just makes the wrong estimate more certain. A third example is that systematic missingness by subgroup can distort subgroup comparisons even with large denominators because the missingness mechanism changes who is represented in each subgroup. Precision and accuracy also interact when you communicate results because people often interpret high precision as high trustworthiness. High precision is valuable, but it can create overconfidence if accuracy threats are not discussed. For example, a very narrow confidence interval around an outcome rate can look convincing, but if the outcome is underreported in one site due to documentation differences, the rate may not be accurate across sites. Another example is a highly precise model estimate of an association that is confounded by a key unmeasured variable, making the estimate inaccurate as a causal effect. A third example is a precise time trend that is actually driven by a coding change, making the trend inaccurate as a representation of real-world change. This is why careful reporting often pairs numerical uncertainty with a discussion of data quality, measurement, and design limitations. A practical approach to balancing precision and accuracy is to treat them as two separate checklists. For precision, you look at denominators, event counts, standard errors, and confidence intervals, and you evaluate whether estimates are stable enough for the decisions being made. For accuracy, you look at selection, missingness, misclassification, coding consistency, and whether the sample truly represents the target population. For example, you might decide a subgroup estimate is too imprecise to work because it is based on very small counts, even if it is accurate in expectation. Another example is you might decide an estimate is precise but needs a strong caveat because the sample is not representative of the population you want to describe. A third example is you might decide to use standardization or weighting to improve accuracy of population inference, accepting that these steps may reduce precision slightly by increasing variance. This mindset helps you make trade-offs transparently. Finally, precision versus accuracy is central to interpreting comparisons. A small difference between groups can be statistically distinguishable in a large sample, meaning it is precise, but it might still be practically small or influenced by systematic bias. A large apparent difference in a small sample might be practically important but uncertain because it is imprecise. The skill is to hold both ideas at once. How certain is the estimate, and how believable is the estimate as a representation of the truth you care about? Examples include comparing rates across regions where coding differs, comparing outcomes across sites with different case mix, and comparing time trends across years when data captured changed. Precision tells you about stability. Accuracy tells you about validity. You need both to support inference that is useful and responsible. Design-based variability is the extra uncertainty that comes from how data are collected, not just how many observations you have. Many standard formulas for standard error assume a simple random sample where each observation is independent and equally informative. In real-world biostatistics, that assumption is often wrong. Observations can be clustered, meaning units are grouped in ways that create correlation, such as patients within clinics, students within schools, or repeated encounters within the same person. Data can also be weighted, meaning some observations represent more people than others, as in many surveys. Clustering and weights change how much information the sample truly contains, which changes standard errors and confidence intervals. For example, 10,000 records from 10 clinics can carry less independent information than 10,000 records spread across 200 clinics, because within-clinic observations tend to be similar. Another example is a survey where a small number of respondents represent large population segments through high weights, which increases variability. A third example is a data set with repeated measures per person, where treating visits as independent can artificially inflate sample size and understate uncertainty. Clustering increases variability because observations within the same cluster share similarities that reduce independence. This similarity is often described by an interclass correlation, meaning observations in the same cluster tend to be more alike than observations in different clusters. When interclass correlation is greater than 0, the effective sample size is smaller than the raw count because you have fewer truly independent pieces of information. For example, outcomes in the same clinic can be correlated because of shared clinical practices, shared documentation workflows, and shared patient mix. Another example is outcomes within the same person across time, which are correlated because the person's underlying risk factors and circumstances persist. A third example is geographic clustering, where individuals in the same area share environment and resources. If you ignore clustering and treat all observations as independent, standard errors can be too small and confidence intervals too narrow, which makes results look more certain than they are. A practical way to think about clustering is to separate the number of observations from the number of independent units. If the true independent unit is the person, but you analyze encounters, you have multiple rows per person, and your effective information is closer to the number of people than the number of encounters. If the true independent unit is the clinic, but you analyze individual patient records without accounting for clinic clustering, you may overstate certainty about clinic-level comparisons. Examples include analyzing multiple laboratory results per person as if they were independent, which can make p-values artificially small. Another example is comparing clinics with many patients, where within-clinic similarity can produce overly confident estimates if not handled properly. A third example is analyzing students within schools where school-level factors drive outcomes, which requires acknowledging that the school is a shared context. Recognizing the true clustering structure is one of the biggest steps in getting inference right. Weights change variability because they change how much each observation contributes to the estimate. In many surveys, weights exist because some groups are oversampled or have different response probabilities, and weights are used to make the sample represent the target population. When weights vary widely, a few observations can have very large influence, which increases variance and therefore increases standard errors. For example, if a small number of respondents represent a large segment of the population, any random variation in their responses has a large impact on the weighted estimate. Another example is a design that intentionally oversamples a subgroup. Weights correct the estimate back to the population, but the variability reflects the design. A third example is non-response adjustment weights, where weights increase for underrepresented groups, which can improve accuracy of population inference, but can reduce precision if the weight variation is large. Weighting is often a trade-off. It can improve representativeness while increasing variance. Clustering and weights often appear together, especially in complex survey designs that use multi-stage sampling. In such designs, respondents are sampled within clusters, and then weights reflect selection probabilities and non-response adjustments. Inference in these settings should respect both the clustering and the weights to avoid misleading standard errors. For example, treating a complex survey as if it were a simple random sample can underestimate uncertainty because it ignores that respondents came from a limited number of clusters and that weights concentrate influence. Another example is comparing subgroup estimates without design-corrected standard errors, which can make subgroup differences appear more certain than they are. A third example is trend analysis with repeated survey waves, where design features can differ across waves, and ignoring those differences can distort comparisons of uncertainty across time. The practical lesson is that design-based variability is not a minor technical detail. It changes what you can reasonably conclude from the data. Design-based thinking also affects how you should visualize and summarize uncertainty. When clustering and weights are present, confidence intervals should reflect design-corrected standard errors, not naive ones. This matters in plots with error bars, in comparisons across groups, and in dashboards that report uncertainty. For example, a mean and confidence interval plot that ignores clustering might suggest two clinics differ significantly when the difference is within design-based uncertainty. Another example is a time series of weighted rates, where the uncertainty bands should reflect the weighted design. Otherwise, the bands can be too narrow and lead to overinterpretation of small changes. A third example is a subgroup bar chart, where the apparent ordering of groups might not be stable once design-based variability is considered. Visuals that show uncertainty are only as honest as the standard errors behind them. Finally, design-based variability is a reminder that more rows is not the same as more information. If rows are highly correlated, the effective information grows slowly. If weights are extreme, effective information can be concentrated in fewer observations. This is why you can have a data set with millions of rows and still face important uncertainty for certain comparisons, especially small subgroups or cluster-level effects. Examples include a large administrative dataset where the outcome is rare in a small subgroup, producing high uncertainty despite large overall size. Another example is a multi-site dataset where the number of sites is small, limiting inference about site-level variation, even if each site has many records. A third example is a weighted survey where a subgroup estimate relies on a small number of heavily weighted respondents, making it unstable. Understanding design-based variability helps you choose appropriate methods and communicate results responsibly. Simulation is a way to learn sampling and variability by creating repeated what-if-we-did-this many times experiments on a computer. It turns abstract ideas like sampling distributions, standard error, and the central limit theorem into something you can see and measure. The core idea is simple. You specify a population or a data generating process, draw many samples from it, compute the statistic of interest each time, and then study how that statistic varies across samples. This directly matches the definition of standard error as the spread of an estimate across repeated samples. For example, you can simulate drawing many samples from a population with a known mean and see that the sample means cluster around the true mean with some spread. Another example is simulating a binary outcome with a known probability and seeing how the sample proportion varies when sample size is small versus large. A third example is simulating event counts over person time to see how rate estimates fluctuate when events are rare. Simulation is especially useful because it lets you explore situations where formulas are less intuitive. Many people can memorize that standard error decreases with the square root of sample size, but simulation helps you feel what that means. For example, you can simulate samples of size 25, 100, and 400 and watch how the distribution of the sample mean tightens as sample size increases, showing the square root improvement pattern. Another example is simulating a skewed population, such as a log normal cost distribution, and seeing that individual data are highly skewed, but the sampling distribution of the mean becomes more symmetric as the sample grows. A third example is simulating a rare event with probability 0.01 and seeing that sample proportions are often zero in small samples, which makes the distribution discrete and non-normal. These experiences make it easier to understand when normal approximations are reasonable and when they are not. Simulation is also a clean way to study bias versus variance, which connects directly to accuracy versus precision. In simulation, you can define a true parameter, like a true mean or true proportion, and then compare the average of your estimates across simulations to the truth. If the average estimate across simulations differs from the truth, that indicates bias, which threatens accuracy. If the estimates vary widely across simulations, that indicates high variance, which threatens precision. For example, you can simulate a measurement process that adds random noise and see that estimates remain unbiased but become less precise. Another example is simulating a selection process that oversamples a subgroup and seeing that estimates can become biased if you ignore weighting, even if they are very precise. A third example is simulating misclassification of a binary outcome and seeing that estimates of prevalence can shift away from the truth in a consistent direction, creating bias that does not disappear with larger sample size. Simulation helps you separate what more data can fix from what only better design or measurement can fix. Simulation can also teach design-based variability in a very direct way. If you simulate clustered data, you can see how treating clustered observations as independent leads to standard errors that are too small. So, for example, you can simulate multiple individuals within clinics where clinic-level effects create correlation, and then compare the variability of estimates when you properly account for clinics versus when you ignore clinics. Another example is simulating repeated measures within individuals and seeing that analyzing all measurements as independent makes uncertainty look artificially small. A third example is simulating weighted samples where some observations represent many people and seeing that weight variability increases the spread of weighted estimates across simulations. These simulations make effective sample size feel real because you can watch uncertainty behave as if the sample were smaller than the raw row count. Another major value of simulation is that it supports method checking and intuition for confidence intervals. A confidence interval is meant to capture the true value a specified fraction of the time under repeated sampling, which is called coverage. Simulation lets you check coverage by building confidence intervals in each simulated sample and then counting how often those intervals contain the true parameter. For example, you can compare a normal approximation confidence interval for a proportion to an alternative interval in rare event settings and see that the normal approximation may undercover when sample size is small or when the proportion is near zero. Another example is comparing intervals for a mean under heavy skewness, seeing that some intervals behave better than others at modest sample sizes. A third example is seeing that confidence interval width responds to sample size, outcome variability, and design effects, reinforcing the earlier ideas about standard error. This turns confidence intervals from a formula into a repeated sampling concept. Finally, simulation is a learning tool that builds transferable intuition because it is not tied to one dataset. Once you understand how to simulate a population, sample from it, and study variability, you can apply the same reasoning to many problems. For example, you can simulate the effect of changing sample size on the stability of subgroup comparisons. Another example is simulating how rare event rates fluctuate month to month, which helps you interpret time series plots without overreacting to noise. A third example is simulating how different levels of clustering change uncertainty, which helps you plan designs and interpret multi-site data. Simulation trains your statistical instincts by letting you see repeated confirms of the same principle. Sampling variation is real, standard error quantifies it, design affects it, and sample size influences it in predictable but not magical ways.